going to turn this down a little bit. So we're trying to film these lectures here. So that's why we have the camera, and I'm wearing this microphone. So if I'm not loud enough, you can't understand what I'm saying, just let me know. I'll try to speak up a little bit more. And so, first of all, welcome to the 2014 cell modeling workshop, or workshop for spatial realistic simulations of microphysiology. So we'll have a little bit of a meet and greet. So we'll introduce ourselves, and you will ask that you introduce yourself, so we can actually get a bit better feeling for what kind of things you're working on, what kind of questions you have. So it's kind of nice for us to understand what kind of problems you're trying to solve using our tools. And that'll also help us to hopefully make good decisions in the future, what kind of things we need to develop better or more, or what things are missing still. So it's really quite important for us to know what you guys are up to. And so please also, if during the workshop over the next 3 days, if there's something you think is missing, or it doesn't, something that would really help your research, let us know. We really want to know how the tools are working for you, how everything is working out for your research, and if something's missing or not working well, please let us know. We really need your feedback. We'll also probably give out a survey sometime tomorrow where we'll ask those questions, but just talk to us. There's many of us around over the next 3 days, so please don't be shy. So this workshop and the development of all the things that we will talk about in the next couple of days is part of a center, a National Center for Multiscale Modeling of Biological Systems. So first of all, my name is Marcus, by the way, so we'll introduce the rest of the crew. I work here at the Pittsburgh Supercomputing Center. I direct a group here called the Biomedical Applications Group that does a number of biomedically related projects. And this center, MM Biocenter, let me just go all the way through here, was established 2 years ago with a real focus on developing new methods for signaling, neurosignaling system. And it's a collaboration between a number of institutions. We have the Salk Institute, we have University of Pittsburgh, we have Carnegie Mellon University. So it's a collaboration across the United States, a very, I think, productive and very nice collaboration. Different people with different expertises working on different kinds of tools. And the goal here really is to come up with new ways to simulate biological systems across, ideally, a whole range of scales. So many of you might be aware of the fact that one of the big challenges we still have is that many of the approaches we're developing or that we have are really focused on a specific scale, the molecular scale, the cell scale, the tissue scale, and so forth. But it's very difficult to actually connect across these scales. And one of the goals that we have, and this workshop actually is sort of a first attempt, I think, toward this goal, is to connect these tools better, to develop ways that you can take approaches at the cell level, say, and combine it with approaches that people have come up with to study how tissues are built or cells are structured. And so basically, we have here that subcellular scale. We'll talk more about this later on. We have here the level of whole cells or even whole neural circuits. And so the focus of this workshop really is on these two aspects, where we want to combine realistic simulations of, and we'll talk more about what this actually is, of cellular systems with methodologies that really help you determine how these systems actually look like, how they're composed, where the molecules are located in these systems, and how they're built. And so hopefully this will become a little bit clearer as we move, as we go forward. So just to give you a very high-level overview of what's going to happen over the next 3 days. So what we want to do is really to introduce you to a spatial simulation workflow that really will hopefully allow you to start with the question that you have, whatever that might be. You want to study some signaling pathway, you want to study some neural system, or whatever the question is, and maybe we'll find out what that is when we go around and have yourselves introduce yourselves. And so the components of this pipeline are a couple of tools and methods that are developed right now as part of this MM Biocenter. So today, on day 1, we'll focus on MCell, which is sort of the simulation engine that does these spatial realistic stochastic simulations of these subcellular or cellular systems. There's a tool called Cell Blender that we have developing and made really nice strides over the last 2 years, I think, which is sort of a GUI for MCell that allows you, in a graphical way, set up MCell simulations and to run them, and at this point also to analyze them a little bit, and it'll keep getting more powerful in the future. So this is what we'll cover today, mostly on day 1. So I'll start this morning with an introduction to Cell Blender, introduction to MCell. Tom will tell you a little bit before lunch about Cell Blender, what it is, what you can do with it. And then in the afternoon, we'll have really hands-on tutorials where you can all try them out yourself. We have some canned examples. For those of you who have a research question already, who want to actually start working on their model, that's, of course, even better. So, and you're welcome to start doing that this afternoon or tomorrow, and ask us questions if there's any problems you encounter. Then tomorrow, on day 2, we'll go a little bit into rule-based modeling. Jim will take the lead tomorrow on that. And basically, this is a way for your models to deal with the complexity that often arises if you have complicated reaction networks. So you have this combinatorial complexity of many reaction partners, many intermediate states, and you really, at some point, arrive at a situation where you just even can't write down all the reactions anymore explicitly. It's just too complicated. You have too many. It's impossible. And there's very efficient and good tools that are being developed called rule-based approaches that really help you with that. It's a different way to formulate your question without having to think about all the reactions that are really happening. Rather, you write rules that describe what could happen in the system, and what happens in an actual simulation really depends on how the simulation proceeds as a function of time. So it'll become more clear, I hope, tomorrow when Jim will talk about this. And this is also integrated in the workflow that we have, so you can create a rule-based description of your simulation system and can actually export that into and simulate that in MCell. So this is possible. And so on day 3, we will cover a very interesting approach really for one way to come up with information regarding the way how your system looks like and where the molecular players are located. So these are machine learning approaches based on imaging data that allow you to actually build what's called generative models of how your system, basically what your system is composed of, its structure and its molecular composition. So you can learn these models, and you can actually use them to generate any number of geometries that are drawn from this generative model. So it's a very powerful way, if you have access to this kind of imaging data, to develop instances of possible instantiations of your model that you wanted to simulate. And again, you're able to actually import these types of models, in these types of generative models into an M-cell simulation, actually then simulate them. So it's a number of ways you can actually end up with a spatial simulation that will eventually run in M-cell. And what the right way is for you, and we'll talk more about this as we go on, that really depends on the question that you have. And so these are just possible alternatives, possible paths that you could pursue to come up with a model of your system, and which is the right one depends on the question that you have. And I'll touch more on this as we go on. So this is sort of the high-level overview of what's going to happen in the next 3 days. So we'll talk about a lot about M-cell and Cell Blender today. We'll talk about rule-based modeling tomorrow, and we'll talk about generative models of cell organization on day 3, and we'll tell you how this all integrates with our M-cell modeling framework. Are there any questions at this point? So we would like to keep that interactive. So if there's anything unclear or you have questions, interrupt at any point in time. So, okay, so to end this intro, let me just, I hope I didn't forget anybody. But so it's actually a fairly sizable team that's working on all that. And so maybe I'll just introduce people in order here. So we have Tom from the Salk Institute. We have Deepak. I haven't seen Deepak yet, so he'll be introduced later. Jacob over here. Myself. There's Jim in the back, Jim Fader. We have Bob sitting in the back here. We have Bob Murphy, he isn't here yet. We have Devin in the front and Jose in the front. So these are all people that will help you over the next 3 days with your M-cell and Cell Blender and BioNetGen and Cell Organizer questions. So feel free to approach any of us at any time with questions. Some of us are probably more skilled with certain aspects, so if somebody doesn't know the answer, hopefully somebody else will. Okay, so why don't we go through real quick? Why don't you maybe briefly just introduce yourself, name, institution, and maybe summarize briefly why you're interested in this type of modeling. Maybe you have a concrete research question already. If not, maybe just tell us why you think this is interesting to you or important for your research. So maybe we'll start with you.
I came to this workshop because I see much potential in this program. Yeah. So I plan to use it in my futures.
Okay. Well, Margaret presented me. I'm Jose. I'm working with Dr. Feder in the University of Pittsburgh. I have been working on making the link between BioNetGen and Cell Blender, and how to get reaction networks from other sources, existing biological knowledge of biochemistry, and get that into spatial modeling. So I will introduce you guys to the if you have any questions.
I'm Devin. I work in Dr. Murphy's lab, and I've been working on the link between Cell Organizer and M-cell, and what that allows you to do is to learn generative models of geometries, specifically cellular geometries, and then in an automated way synthesize new geometries and link them up with reaction networks for simulation in a high throughput manner.
I'm Peter. I'm a third-year neuroscience student, graduate student in Computational lab at University of Maryland. And I'm interested in mechanisms that regulate transmembrane protein retention and mobility in the neural synapse. There's a lot of work showing that the geometry of the spine, the neural spines can change a lot. It's unclear how that can influence the retention of mobility of these very important proteins. I'm trying to see if I can simulate some of that. Predict what can happen.
Mm-hmm.
Hi, my name is Ashwin. I'm from Washington University in St. Louis. I'm a postdoc with Dr. Yoram Budi. I actually used MCell 3.1 about 6 years ago, and then kind of moved on to doing other things. I mean, so when I kind of used MCEL previously, it was studying neurotransmitter gradients and homeostasis in and around the synapse. I since moved to cardiac arrhythmias, and now we're interested in understanding calcium dynamics with some cellular domain, which is why I'm kind of thinking maybe MCEL would be a good fit again. So that's why I'm here.
I'm Christine. I'm from University of Queensland, Australia. I'm a postdoc in my lab there that looks at GABAergic synapses. So I've got a very specific question I want to answer. I've got one GABA receptor that gives a really unusual postsynaptic current, and I want to understand whether that's because of the spread or concentration of the neurotransmitter, or whether it's because of the position of the recipient. So I want to investigate the relativity of the system.
Hi, my name is Murugesh. I'm a PhD student at Purdue University, working with Dr. Kim Wilson. I'm interested in calcium-dependent insulin-based disease data.
Hi, my name is Jo. I'm from I'm working on the beta mechanism transformation in the P3 sensory system. So in the P3 sensory system, there are lots of specialized synaptic structure. So I'm very interested in how that kind of synaptic structure can yield any interesting structures for the beta transformation. I'm mainly a experimentalist, so I'm doing catch time recordings. So my modeling time is always being delayed because I hope this workshop could give me a chance to do that time.
Very cool. Good.
My name is Tom Hartall. I'm one of the co-developers of MCEL. It started as part of my PhD thesis project in 1985. And here we are all these years later. And originally it was designed for studying the neuromuscular junction. I studied this in my thesis project. And then when I went to the Salk Institute,
Okay, so that's a wide variety of different projects, so that's actually really cool. So again, if you have any questions for us over the next couple of days, don't hesitate to ask. Are there any questions before we go ahead that you have? So there's an agenda up front here. So the plan for today, this morning, is we'll have a lecture now sort of on call it Introduction to M-Cell. Then we'll have a break. There's another lecture that goes a little bit more into the methodology. Hopefully there's time for that. And then we have a lecture, an intro and demo on the use of Cell Blender and the kinds of things you can do with that by Tom. And then we'll have a lunch break. So lunch is usually around the corner in this little room outside here. And then we'll go next door. So next door is a computer lab. And that's where we do the hands-on sessions. You're welcome to use your laptops, but there's desktops provided, so whatever works best for you. So either way is fine. Okay, so we'll get started. Just so the slides and all the other slides of all the other speakers are available online or will be available online. So I'm not sure if these are available yet, but they will be within the next hour or so. So there's no need for you to take extensive notes. You don't have to. So everything will be available. Okay, so the goal of the next lecture basically is a high-level introduction into M-Cell, which is our spatial stochastic simulator. So we'll talk a little bit about sort of just the general workflow, how you would go about developing a model for M-Cell, what the components are. We'll talk a little about pitfalls maybe and things you need to think about. And then we'll spend a little bit of time talking about the syntax of the language that M-Cell uses to describe its models. So M-Cell has something called model description language, which is kind of like a programming language that allows you to describe your model. What the geometry looks like, what molecules you have, what reactions you have. So this is, so the good news is really that we have this tool now that's called Cell Blender, which is a GUI, a graphical user interface that basically allows you to set up simulations without knowing very much about this language at all. So if you're lucky, you can do everything in this graphical user interface. You put in your molecules, you add in your reactions, you can make a geometry. And so if you're lucky and depending on the questions that you have, this might be enough for you to set up a model and to run it and to get results. And you may never have to actually see this model description language. For some of you, if you want to go to more sophisticated models, at some point it's probably necessary to look at this language a little bit because some of the things may just not be in the GUI yet, or it may be not convenient enough. And my personal opinion is, but that's my personal opinion, is that it's always good to know what goes on under the hood if you really want to do this as a career. And so if M-Cell really becomes a critical part of what you're doing as part of your research, I think you have to know a little bit about how this language looks like, what M-Cell can do. It'll really help you make good and powerful models, I think. So so there's no requirement that you absorb everything I say. It's mostly just a high-level overview. You kind of see what's possible, how things are done. But I think if this really becomes your main modeling tool, it's good for you to know about that. And you actually need to know more than I will talk about. And there's certain aspects of this language that really are deep within the modeling philosophy of M-Cell, how things are described in a spatial simulation environment that you can't even escape in the GUI. So once you involve space, things become much more complicated than you would think. You have to think about the inside and the outside. You have to think of different compartments, what molecule is in what compartment. So things can become very complex very quickly, and even just describing that even from within a graphical user interface, is not necessarily easy, and you really need to think. So we'll come to that. But so that's sort of my justification why I still talk about MDL, even though, you know, we have this nice GUI, but I think it's still good to know for you guys. Tom, please.
And then the really much bigger picture, if you're going to be a computational biologist, the computational part of that becomes really important. And really what you need to consider is, you know, how much you need to know about how computers work, and computer programming. And you know, Marcus and myself and Jim's students are computational biologists, and they're programmers. We're all programmers, and we built MCell and bionet language and cell organizer to perform these tasks that there was no tool yet provided to do, and so we had to invent those and do that ourselves and program the computer to do it. And these tools are open source, and you know, when we started, these tools weren't available. We invented them. They're available now for you to use, but they don't do everything, and there's a whole universe of things yet to be done in studying how cells work, and more software needs to be written. And these tools are open source and available and extensible, and we invite you, any of you who want to, you know, build your own tools or help us extend these tools to do so. And to do that, you have to learn how to program a computer. And so,
Yeah.
so the model description language that MCell has is just one aspect of interacting with the computer to make the computer do what you want to do. But as you go deeper, you might have to actually do things that no tool can do yet. You have to program the computer to make it do those things.
Yeah. I forgot to mention, and Tom reminded me, so the tools, MCell, CellBunder, they're all freely available, so you can just go to either mcell.org or mmbios.org, and you can download them. So they're freely accessible to you. If you go to mmbios.org, we also have, now for a couple months, we have a forum, a user forum. So if there's any questions, so this is really the best way for you to get in touch with us. So just create an account, and we can show you where that is on the website, and then you can ask questions. Usually one of us monitors what's going on, so that's a good way for us to interact. So we prefer that much more than if you send us email, because that way, you know, more people benefit from the answers that we give. So this is really a good way to get in touch with us. All right, so I need to press on so we can actually make some progress. So just a reminder, so MCell is a simulator that's specifically geared at modeling complex 3D spatial geometries, and what this really means depends a lot on the questions that you have. So this is one possibility, so you can see it can become very complex, and Tom will show you a movie, I think, later and talk more about this. So this is a very complex piece of tissue from the brain, has many synapses, has a lot of spatial complexity that may be critical, or is probably critical, for the actual biology that underlies this system. So this is just to show you what complex could mean. And so this is really something that's not a problem at all for MCell to simulate. So complex spatial geometries are something that MCell is really good at. And so the three components that any MCell simulation consists of is geometry. So you have to have some kind of geometry, and we'll talk a little bit about briefly how you can get this geometry. There is random walk diffusion, so you have particles, molecules that diffuse in space according to diffusion coefficient. And you have reactions between these molecules. And so in MCell, these molecules can either diffuse in the volume, so volume molecules, or they can diffuse on a surface. So it can be diffusing surface molecules. This could be channel membrane proteins or whatever, membrane receptors. And you can have reactions between volume molecules, between surface molecules, and surface and volume molecules. So all combinations are possible. Okay, so this is basically, in a nutshell, the main ingredients in an M-cell simulation. And we'll go through all of these briefly and talk about what these really are and how you can get at those. And so the kind of workflow that most people, and you included, will probably go through to develop an M-cell model is you have to obtain or create some kind of geometry of your model. So this is step one typically. Doesn't have to be, but often is. Then you have to annotate these meshes. And what we mean by annotate is now that you have a spatial model, you have to decide where in your model these molecules actually are located. So this is often not necessarily an easy question. So you want to release molecules in your system. Are you going to release them everywhere? Are they confined to a compartment? Are they confined to a membrane patch? Are they on the whole membrane? So you need to think about where these are in your three-dimensional geometry. And so this can have a big impact on your actual simulation. You need to specify what I call non-spatial model parameters. So these are diffusion coefficients, reaction rates, whatever describes your simulation. Then you will simulate your model, and then typically you'll look at it and you'll analyze the results. Often this is sort of an iterative process. You may have sort of a starting model. You simulate, you look at some of the results. You may have some experimental constraints that tell you if this is a good model or not. And if not, you may tweak some of the parameters, do it again until you have something that looks or agrees with what kind of whatever constraints you might have. One thing I wanted to really emphasize, if you have a spatial model, it's really critical that you look at it. So I can't stress this enough. If you simulate your M-cell model, especially initially when you're starting to just design it and you kind of think about how it should look like, it's critical that you look at it in Cell Blender. It's very easy to make a mistake. You place a molecule outside the compartment accidentally, it's not inside, and of course your whole biology is different now. And so it's extremely easy to make these mistakes, especially when surface molecules are involved and you have transport processes going out or into a compartment. So it's critical that, especially in the design phase of your model, you look at it very carefully, all the time, very often. Once you're done with designing the model, you're just running it. You don't have to look at it anymore. But until that point, you have to be, you should look at it as much as you can. So this is really critical. I mean, some people, they make a model, and then it seems to run fine. They get some results. It looks beautiful. And then, months later, they realize that the molecules that they have released in the model are not anywhere close to where they should be. They're just somewhere else. And so, of course, the whole reaction dynamics model is a completely different process. And so it's really, once you go spatial, things become a little bit more complex, and you have to really make sure that the model really that you've designed really agrees with the kind of model you wanted to build in the first place. All right, so let's talk very briefly about geometry creation. So this is the key step. How do you get the geometry for your model? I don't want to dwell on these points too much. I just wanted to mention them. Two of these methods we'll talk about in more detail. Tom will probably talk a little bit more about the first one in his presentation. The first one is that you actually use electron microscopy imaging to reconstruct part of the tissue that you're interested in. So somebody goes through the motions of actually taking a tissue sample, putting it slicing it finely, taking pictures using an electron microscope, going through the motions of registering this image stack and segmenting it, drawing where all the important parts are. And then you can actually use that as an input geometry for your M-cell model. And so the picture that I showed initially, and Tom will talk more about this later, this one here is from a reconstruction, right? From a reconstruction from real brain tissue. And this is a very good way to get a very detailed and precise geometry for your model simulation and for some questions, this may really the only way you can get a realistic representation of your system. So this is one way. It's, of course, very time-consuming. So somebody needs to do the work of imaging, reconstructing, segmenting. That can take a year or half a year. So it's by no means an easy way. But it's a good way to get a good geometry. Then the second methodology, and this is actually a method that we'll talk about on day 3 a lot more, and maybe also the next couple days, is to use generative models to get geometries of cells or whatever you might be interested in. So this means, and so this uses fluorescence imaging microscopy of whatever tissue it is that you're interested in, and learns basically the shapes and distributions of molecules in your system, and you can then use this model to create cell shapes and locations of molecules, and you can actually sample them statistically. It's a very nice way, if you have access to this kind of data, to create models that you can then simulate in M-cell. Okay? So we'll talk more about this in a bit. And then there's another method. That's one that I use a lot, and this is something that you'll actually do this afternoon, basically using CellBlender, is that you design your geometry in silico using CellBlender based on experimental average geometries that you might have. So you might have this kind of freeze fracture M data, so you know, so this is actually an active zone of a synapse, and you might know, well, this active zone is a micron long, it's a half a micron wide, there's so many vesicles, the vesicles have 50 nanometer diameters, and so you can use that information to build a model in the computer. So it's an average model of how the system looks like, and use that as input for your M-cell simulation. And so this is actually a very quick and easy way to get potentially a very detailed and powerful model of your system. So if you have this kind of knowledge of how your cell looks like, how your compartment looks like, how your synapse looks like, whatever you're interested in, this is a very good way to get an M-cell simulation that can be quite powerful for predicting whatever you're interested in. So this is probably the fastest way to go from nothing to something. And this is basically what we'll do this afternoon. CellBlender is a really good tool to make these kinds of geometries. So once you learn how to use CellBlender, you can make a fairly complex geometry within an hour or a day. So it's very quick. But of course, you need to know something about your system. So it's not some Mickey Mouse thing, right? I mean, you have to have some knowledge about what your geometry looks like, at least in an average sense. You need to know dimensions, numbers, distributions, right? So these are basically the 3 typical ways to get at a geometry, and we'll touch on all 3 within the course of the next 3 days. This afternoon, you'll actually use CellBlender to create a geometry completely in silico that you can then use to simulate, and that you can do fairly quickly. So this is the beautiful thing about CellBlender. So you can actually come up with fairly complex and realistic geometries after a little bit of practice with the tool in a couple hours, basically, or even less. Are there any questions about this geometry thing? How you get geometry for your model? So this is a really sort of critical part of designing your simulation. So you need to think about what is your question, what is the geometry, what would be a good way for me to get at this geometry. Maybe you have some experimental data, then you should think about how can you utilize that information to build that model. Maybe you have a general understanding of how the system looks like, you know the approximate dimensions, you know the volume maybe, or you know kind of it's between this and that, and then you can use that also to build your models and kind of investigate, for example, how does the dimensions or the structure of your system affect the biological dynamics of what's happening. Ashwin, you had?
Yeah. I had one quick question on the cell organizer, the second one. So if I just understand it right, so if you have fluorescence data and if you feed it to cell organizer, it could reconstruct.
I'll defer to Devin, who is the.
Yeah. So if you have fluorescence microscopy data, you
it's a package by itself that will take your data
and then create a model that allows you to generate new instances in silico that are not necessarily the same as the observed instances, but are statistically represented. So,
But is that 2D or 3D?
It works in both 3D and 2D.
Yeah, this is actually a good point. So, you know, whenever we design these geometries, you have to keep in mind that in real biology, you never just have one geometry, right? I mean, they're very more or less, and so you have to always keep that in mind. If you design a geometry, what is that really? Is that the average geometry, or have you accidentally picked an outlier? That's, you know, might happen once in a while, but it's not really representative. So it's always good to think about this a little bit. And so with the cell organizer, for example, you get a real statistical distribution of possible geometries. So you know, if you pick 100 geometries from that cell organizer gives you, you have a pretty statistically a good representation of how your system looks like. Right? If you do a reconstruction from EM, you know, you're probably hoping that what you reconstructed is a good representation of an average neuron or synapse, but you know, you don't really know. I mean, you may have, and so again, for this process, you typically try to find ways to get good average descriptions. You might look at many freeze fracture EM tomograms just to kind of see, okay, how does it vary? And then you decide, well, this looks like a good average structure. So it really depends on the question that you have. But, okay, so let's move on. So this is the geometry. So after going through one of these 3 steps, you have some kind of geometry that you think represents your model. Now you need to think about some additional parameters or components of your model. One of them are molecules. There's presumably some molecules floating around in your simulations, or floating on, or in being in the membranes of your simulation. So you need to know, what are these? Where are they located? And so again, where are they is sometimes not necessarily an easy question to answer. So you need to think about, you know, where are they on the surface? Where are they in the volume? And of course, for each of these guys, you need to know the diffusion coefficients, and you need to know the concentrations and densities with which these are distributed within your system. So this is kind of information you need to know that often comes from literature, but maybe you have some experimental data that will help you get at that information. If you have a generative model from Cell Organizer that will actually give you the concentrations of your components in the different compartments. So you need the molecules, you need the reactions between these molecules, so you need to know what's going on, so what is reacting with what. And again, I mentioned already, these reactions can happen either between volume molecules, between surface molecules, and between volume and surface molecules. And for these reactions, you need to have the reaction rate constants. And this is a little bit more of a difficult thing to come up with, because they're often not necessarily known well. For some reactions there are, for some there aren't. And so again, they typically come from literature, or maybe some of them remain parameters, and you have to play a little bit with your model to figure out which are good values that seem to generate a model that agrees well with the experimental data that you have. And then one additional complication that arises here is that there are situations where you have so many reaction partners and things become so complex that it's actually very difficult to even write down all the reactions explicitly, because you might have molecules that have oodles of phosphorylation states. Each of them can be phosphorylated, unphosphorylated, and to model this explicitly with reactions, you get a combinatorial explosion. So you might have 10 to the power of whatever reactions to write down. And so if that doesn't necessarily happen routinely, but it can happen, especially if you have complicated signaling pathways. And so here is really where BioNetGen with its rule-based approaches, can really help you deal with that complexity. So you don't have to really think about all the different reactions. You just think about things that can happen and formulate them in rules. And Jim will explain how that works tomorrow. And if that's the case for one of your models, we can deal with that, and you can use BioNetGen to import into MCell these rule-based descriptions for your reaction. So that's possible. So you don't have to write them all down by hand. The final thing that you need to think about is what I call output specification. So you need to decide what kind of output do you want from your reaction. And again, this is, since we are in a spatial domain, this is a little bit more, you need to think about this a little bit more in detail perhaps. So you might be interested in the concentrations of molecules A, B, and C everywhere, but maybe you want to be a little bit more fine-grained. Maybe you want to know the concentration in different locations in your system. Maybe there's a concentration gradient. Maybe you have some non-steady state going on. So just measuring the total concentration may not really tell you about this. So you need to think about, how do I need to measure in my system so I can really answer the questions that I have. And so this is all possible. So you can basically sample any kind of thing you want anywhere in your simulation at whatever spatial level you want. So it's easy to do in MCell. You just need to think about what your question really is. Okay, so at this point, you're basically done. You have a geometry, you have molecules, they react with each other. You have decided on a way to measure whatever you're interested in. Maybe the concentration, the density of surface molecules in this membrane patch is really what you want to measure. So now you're ready to run. So in the old days, and I still do it, you would run MCell on the command line in Linux or so MCell is supported on Windows, Mac, and Linux. So whatever you like, you can use whatever platform you like. So your model is described using this model description language. So it's in this file called mymodel.mdl. We'll come to this in a second. And you basically just run it by typing mcell mymodel.mdl. If you use Cell Blender, you just press, it's probably called run simulation or something like that, or run. But just as a reminder, when you press this run button in Cell Blender, this is basically what Cell Blender does for you. You just don't have to do it yourself. So basically, MCell will read your model description, will read your geometry, your molecules, reactions, your output, and just do whatever it needs to do, and then produce output for you, and you can look at it, and you can analyze it. So visualization, typically we do in Cell Blender these days, so this is really the most convenient way, or basically the only way right now to do it. Then we have reaction data output. This is basically the kinds of information, what reactions happened, how many molecules are where. So these are basic text files, and the way you analyze them really depends on you. So Cell Blender has some capability to just plot it for you. If you just want to see how does the concentration change as a function of time, you can do this in Cell Blender. But of course, you may have much more sophisticated questions. You need to do a statistical analysis on the distribution of some molecule in something. So you can then, of course, use any kind of tool you want to use, R, Python, MATLAB, whatever your favorite statistical or analysis tool is. Okay, so this basically is just a reminder, the general workflow that all of you will go through, and we'll start this afternoon actually with some examples. You'll create geometry, you'll put some molecules in there, some reactions, you'll press the run button in Cell Blender, which will run the simulation for you, and we'll look at the result. And so since we have Cell Blender, this is really much more easy now than it used to be in the past. Any questions up until this point? So it may be a little bit abstract, so don't despair. So once you actually use the tools, I think it becomes much more concrete in how this actually works. But I think just so that you see the general workflow, geometry, and then populating with molecules, reactions, thinking about what kind of output you want, and then running the simulation and looking at your output and analyzing.
whether you're using the MDL directly and editing files and typing it in by hand, or using Cell Blender with its GUI-driven approach, that workflow is really the same.
Yeah, it's really...
It's a matter of how you interact with it and create the model, whether you're editing it by hand,
Right. I mean,
in a text editor, or using the GUI.
so for those of you who've done simulations, maybe using ordinary differential equation without the spatial aspect, once you add, I mean, I think I've said that a couple of times now, but once you add geometry, it really becomes, geometry really adds a lot of complexity. So it's good to know and think about your geometry first. How does your system look like? What is what molecules are where do things happen? And then start thinking about, okay, what are the players, where are they located, and where do these reactions happen? It's difficult to think about just your kinetics and forget about the geometry, because if that's the case, then maybe geometry is actually not that important for your system in the first place. So it's good to think about first, how does the system look like, how is it structured, and then put in the different bits and pieces, the parts, add them at the right point positions in your simulation. I think that's a good way to really structure your thinking also and how this model works. Ashwin, you had a...
So just to clarify again, when you say building geometry,
Mhm.
is it still done with Blender or Revit?
This is definitely one way to do it. So MCell doesn't care. MCell just wants a description of the geometry. Blender is a good way to build it from scratch if you kind of know how it's supposed to look like, or you have some information.
Blender is totally different.
Cell Blender is basically an add-on to Blender. So for those of you who've used Blender in the past, we basically use Blender, so Blender is an open source program that's actually designed to make sort of Hollywood-style animations, so movies. It's a tool for making movies. And so it's very good at creating things, spatial things, geometries. Yeah, Tom will show it. And so Cell Blender is basically...
Blender for making
Yeah.
Hollywood-style
Yeah.
movies.
And so we basically use this capability of making these really complex geometries that they need for their movies for our purposes, and add sort of this plug-in that allows you then also to add reactions and molecules. But it's still Blender,
Oh,
right?
it's
Yeah.
Yeah,
Mhm.
yeah,
Yeah. Right.
Cell
Yeah.
Blender is just the name of the add-on that you plug
Right.
into Blender. It's really Blender.
Yeah. Okay, so before we come to the MDL, that I wanted to briefly show you what's actually in an M-cell simulation, I wanted to talk about one thing that's actually very important once you do. This is actually important for any kind of cell modeling, spatial or not, but for spatial it's even more important perhaps. And so that refers to units. And so I've chosen this example here. I could have chosen a different one, but this one's particularly interesting. Anybody know what this is? I've used this last year, so if you read the slides. I should have used a different example. So this is the Mars climate orbiter that was launched in September 1999. Anybody know what happened to this thing?
Why haven't you heard of this since?
Well, basically, to cut a long story short, it basically crashed and burned. And the reason was that the engineers that were working on this thing had a little bit of a miscommunication. So some of them were using metric units, and some of them were using imperial units. And so that just didn't really work all that well. So basically, there was some part of the process where the units didn't match, and so this thing just basically at some point got the wrong command that just basically crashed it. So I don't know how much this thing cost, probably a couple $100 million. So it's a very trivial mistake, right? You'd think that's just stupid. I mean, people should think about units and make sure that if they compute the thrust that's necessary to get into a stationary orbit, that you'd agree on the units. But it didn't happen in this case, and so the result was that it didn't end up in a stable orbit. It ended up on the surface, I guess, or somewhere in the atmosphere.
This is the first.
No, I mean, there's many examples like that. And so the story really is that your M-cell model shouldn't become the next one of these. And you might think, well, but it can happen very quickly. And if you look through the literature, it's riddled with models that have the wrong units, or people take some k values or something from some paper and they forget that the units in this paper are x, whereas my tool uses y, and in no time you're off 2 orders of magnitude because somebody uses different units than you are. So it's very, very important. And we've actually suffered from this a little bit because we're trying to combine our tools. And even our tools, sometimes, you have to be very careful if you do these conversions between, what you have in BioNetGen, what you have in MCell, because everybody, there's no agreed upon units in the community. Everybody has some different units, and you have to be really careful when you design these models that you're careful with the units. So this is just so I'm just going to list them here for you. So and so this is not to say that these are the correct units. These are just the units that MCell uses. So if you use MCell, you got to use these units. And if your K is in a different unit or your D diffusion coefficient, you have to convert it. So they're by no means correct. They make sense, but so basically, spatial dimensions are in units of microns. Time is in unit of seconds. Diffusion coefficients are in units of centimeters squared per second. There's also very typical, it's microns squared per second, so you have to be careful. They're used. Reaction rate constants, unimolecular ones are in per second. Bimolecular reaction rate constants between 2 volume and volume molecules, or volume and surface molecules, are in per mole per second. And for reactions between 2 surface molecules, it's basically similar, but it's a density per second, right? And okay, so these, just keep that in mind. So if you design a simulation, make sure, and you will typically have to scour the literature for some k values or some diffusion coefficients that somebody has determined. Make sure that hopefully they will tell you the units. It's not necessarily given. They might not tell you the units, so then you're in trouble and you shouldn't use them probably. But if they hopefully give you the units, then make sure that they match with what MCell expects. So if you give MCell a diffusion coefficient, it expects that to be in centimeters squared per second. If that's not the case, you'll have the wrong diffusion coefficient. So keep that in mind. So this is really much more dangerous than it sounds. There's a lot of false simulations out there, not just simulations, just false research because of that, because people are off 2 orders of magnitude. And
one of the trickiest things to think about, not to get into too much detail ahead of time, but one of the trickiest things to think about is even if you have all your units straight, when you look at a chemical reaction reported in a paper, there might be reactions where there's actually multiple binding sites for something. And when they write their reaction down, the person who wrote it down is maybe being a little sloppy about the fact that there are 2 binding sites, but the rate constant they're reporting is per binding site or per both binding sites combined together. And there's an ambiguity about it. And I can't tell you how many times we put together a model from numbers in the literature where there's a factor of 2 in one direction or the other, because there's actually 2 binding sites for this thing. So during binding of the first one, of the first of the 2, the rate constant is actually double, but it's ambiguous. You can't tell from the way it's written whether they've already done the multiplication by 2 for you or they haven't, right? And it's just sloppy and unambiguous. And during the first unbinding, when there's 2 bound and the first one comes off, should it be double or half what they report? And so when you finally sit down and do the simulation and you see what the KD is or what the equilibrium concentration is, you realize, oh, they've left off all those factors of 2, and so you gotta take care of
Yeah.
yourself. And then, yeah, so question everything, and check your units, and be careful of tables of numbers and papers and things.
Yeah, so that's really good advice. So just take everything. Don't believe everything you see in a paper. So it's good to make sure you're fairly certain that the parameters you have are good. So one thing also is, once you build a model, you'll probably find that, let's just say you have a model that has 20 parameters, reaction rate constants, diffusion coefficients. You probably realize that maybe 3/4 of them, the exact value doesn't really matter so much for your model, right? So if you double one of them, you still get qualitatively the same behavior, so it changes the numerics a little bit, but it doesn't really change how you would interpret the model. And there might be a few that are much more sensitive. So there might be a few that if you just double them, it really has an impact on your model. And so these would be, especially those would be the parameters you should think about most carefully. The ones where if you double one of your k values and you get a completely different result for your simulation, you would interpret the result differently. So this would be one to think about very carefully and really make sure that you got the right value here. And you might even argue if that's the case, maybe there's a problem in the first place because you wouldn't expect something like that. But it's important to understand your model, how it works, what parameters are sort of more what parameters are more sensitive and which ones are sort of just kind of background behavior. So okay, so let's briefly look at MDL. I'm going to go through this maybe a little bit faster, just to kind of show you how MDL looks like, what's in MDL, and so that if at some point you actually need to look at some of these files, for example, you need to debug something, and you have an error message, and you need to see what happened, or you might want to add some things in there that CellBlender can't do at this point. There's occasions where models become fairly complicated. You need to actually write scripts to automatically generate some models because it's very tedious to do them by hand. So we have a case with Sarah where we place different channels. And so we just write Python scripts that basically create a lot of these files for us automatically because you don't want to write 30,000 lines of reaction data by hand every time. So there's good reasons to know these commands in a little bit more detail. So we have a fairly detailed what we call quick reference guide on mcell.org. So this contains all the commands that are available. So if you use mcell more for your research, it's probably a good place to look at if you don't know what a certain command means, and also just kind of look through at some point to understand what's all in there. So the list I have here is by no means comprehensive. If there's interest, we can also get together sometime in the afternoon or in the evening, and I can go through the quick reference guide, just kind of walk you through. So if there's interest, let me know. We can definitely do that. And so this MDL language is fairly simple. It basically consists of keywords that are all caps and values that are assigned to these keywords, or blocks, MDL blocks that contain a certain amount of content that describe how your geometry looks like, how your molecules, the properties of your molecules. And so we'll just start briefly to look at some MDL. So what we'll do now is we'll build up a model by hand. It's called firstmodel.mdl. It's a very simple MDL file just to show you the basics. And so here are two MDL keywords. One is iterations, one is time step. So these are always required. You need to define a time step for your simulation, and you need to specify how many iterations to run the simulation. The total length is then the number of iterations times the time step, right? Again, time step is in seconds, right? Iterations is just a number. One thing you can see here is you can actually define variables within MDL. So if you want to do that, you can have comments. For those of you who do C programming, these are just C-style comments, but it's not so important. MDL keywords are always all caps. So if you write your MDL by hand, I would recommend don't name your variables all caps because it's just confusing. It's allowed, but it'll greatly increase your pain at some point in the future.
One exception might be
Yeah.
the use of capital D for diffusion constant.
Right.
But other than that,
Right.
probably best to avoid.
Right.
Yeah.
So this is the start of your simulation. You basically specify the number of iterations, 100 in this case. The time step is 1 microseconds. Okay, so we'll start, as we discussed before, we'll start with the geometry. So this is a screenshot of Cell Blender. I've done something that Jim hates. I've created a cubic geometry. So this is not very biological, but it'll do for now. So we have a rectangular cell for now. So it's not very realistic, but and you'll go through how to create a geometry in Cell Blender this afternoon. So we'll just assume we know how to do that. Creating this basically takes about 5 seconds in Cell Blender. So this is extremely trivial to do. And then Cell Blender will create a file called cube.mdl that describes this geometry. So MDL has this ability to include files. So you can have your simulation distributed across any number of files. And this is actually what Cell Blender does under the hood. It's a very useful thing to do. So you can put all your reactions in an MDL file, all your geometry in one, all your parameters in one. So you have them separated. It's much easier to debug and to add if you have it structured that way. You can put everything in one file. It gets kind of tedious, especially the geometry tends to get very plentiful. I just wanted to briefly show you, again, you do all of this in Cell Blender, so you probably never have to deal with it yourself, but it's good to see what happens. And it allows me to talk about one aspect that's actually quite important. So this is how you would describe this cube in MCell. So the details aren't that critical. It consists basically of a list of vertices, right? So the 8 corners of the cube, 1, 2, 3, 4, 5, 6, 7, so and x, y, z. And then you describe how these, so the surfaces in MCell are all triangulated. And this element connections basically describe how these triangles are, describes how these triangles are made up of these vertices. So basically triangle number 1, you connect vertex 4, vertex 0, vertex 3. So here's an example. So this is vertex 0, 1, 2. And you define a triangle by saying this vertex is connected to vertex 1, this is connected to vertex 2, and this is connected to vertex 0 again. So this is how I describe the triangles that make up your simulation. Does that make sense? I mean, you don't have to do that by hand. Cell Blender does it for you. But basically, your geometry is described in terms of little triangles. And these triangles consist each of 3 vertices. Yeah? So there's one, I mentioned this, there's one aspect here that's critical for MCell geometries in particular. So when you connect these vertices to form a triangle, there's a couple of ways you can do it. You can do it either 0, 1, 2 or 0, 2, 1, right? I mean, you can go clockwise or counterclockwise. And the normal vector of this surface triangle depends on how you connect them. So it's the right-hand rule. So if they're connected 0, 1, 2, the normal vector goes this way. If you do it 0, 2, 1, the normal vector would go the other way. So in other words, your surface has an orientation. It knows its direction, right? So then it has a normal vector. This triangle goes up. Right. And so in other words, the order in which these are listed here, the vertices, matters. If you list them that way, it might go this way. If you list them the other way, it might go the other way around. And what's critical is that if you have a geometry in MCell, however you create them, if it comes from, it could come from Cell Blender, it could come from cell organizer, it could come from a reconstruction. You have to keep in mind that your surface has to have a consistent orientation. Otherwise, you have a problem. So basically, let's just assume you create a compartment that's closed, some cell. So then the surface meshes that describe your cell have to have a consistent orientation. They all have to point out, right? So otherwise, you can't define what's inside or outside, right? So all the surface triangles that make up your mesh have to have a consistent orientation. Otherwise, you can't describe the inside or the outside of your cell. Does that make sense? And so if you use Cell Blender, you're in good shape. Cell Blender does that for you. You don't have to think about it, typically. But if you get your geometry from some other tool, you may not be so lucky, right? In particular, for just visual purposes, it doesn't matter, you could argue. You're just looking at the surface. It looks pretty. It's great. And it has the shape of your cell. But just looking at it, it may make no difference how these things are oriented. And so the tools that give you these surfaces, maybe from a reconstruction or whatever you get them from, they don't even care how they're oriented. For them, it doesn't matter. For MCell, it matters a lot. So if you get your geometry in ways different from the tools that we kind of provide, you'll have to be careful. You have to make sure that your geometries have a consistent orientation. And that often requires some hand tuning of your geometry and actually making sure you have a consistent orientation of your mesh. Otherwise, you may have leaks in your mesh because you have non-manifold things in your geometry, for example, where you have one tile that says, oh, the up is here, the outside is here, and you have a tile next to it that says, oh, the outside is here. So at this intersection, there's a problem. So MCell will warn you about some of these, but I'm not sure if we catch everything. So in general, if you're not using Cell Blender or Cell Organizer, some other tool to get your geometry, or you get your model somewhere from a repository, there's repositories that have mesh geometries, you shouldn't assume that the geometry is good enough for an MCell simulation. So you have to really look at it, and Cell Blender can help you with that. And maybe Jacob will talk about this later, or we can tell you about how that works, or Tom. So this is why I mentioned this. So the consistency of the orientation is really critical to define topology. If you don't have that, there's no inside or outside. It's just a mess. It might look good, but it's computationally not a valid description of your topology. So keep that in mind. So if you're just using Cell Blender, that's probably of no concern. But if you have some other source of geometry, you should think about this. And in general, it's always good to check. Any questions about this? And so this orientation is really sort of a key feature of surfaces in MCell. And it'll come, we'll see this again when we talk about surface reactions. So there's this concept that you have surfaces, there's a normal vector, and there's an inside and an outside. Right? Okay, so that's all I want to say about these geometries. A nice thing that you can do also is if you think about this cube, you have all these triangles that make up your surface. You can actually combine any number of these triangles into regions on your surface. So if you have a membrane, say a cell, you can say, okay, these set of triangles is my lipid raft. So I combine these into a region that I call lipid raft 1, 2, 3, 4, 5. So you can actually mark certain surface regions on your geometry so you can basically name them. So you can tag different things on your surface. And you can use that to place molecules or count reactions. So you basically have control over how you want to describe your surface. And if you use Cell Blender, you can do all of that in Cell Blender. So you can basically paint your surface and say, oh, this part is this, and I call it lipid raft. And this part is that, and I call it receptor region, or whatever you want to call it. It's not so important. So I wanted to briefly talk about molecules. So now we have our geometry. We have our cube. The next, so now we know how our geometry looks like. Right? So in this case, it's a simple geometry. It's a cube, so it's not that interesting. Now we can define molecules, and molecules basically consist of two things. They have a name, volume 1, volume 2, surf, and a diffusion coefficient or diffusion constant. And you distinguish 2D versus 3D molecules by giving them a 3D or 2D diffusion coefficient. So if you use Cell Blender to define volume molecules, you just need to give them a name, and you need to give them a diffusion coefficient. You might get that from literature, or maybe have some knowledge of how fast they diffuse. Again, the diffusion coefficients in MCell are centimeters squared per second. So if you get those from somewhere else, make sure that these are in centimeters squared per second. If not, you have to do the conversion. Very simple in this case, but you have to remember to do it. Right, so one thing to keep in mind is these are particle-based simulations that MCell does. So particles, at least volume molecules, are point particles. They don't take up any space. So this is good to keep in mind. So there's no spatial aspect. So we're implementing that. We're trying to provide ways to actually have a space-filling representation, but that makes everything much more computationally expensive. So in a regular MCell simulation, volume molecules are point particles. OK, so now we have defined molecules. There's one key aspect missing, and this is basically in a spatial simulation, it's not enough to just define molecules. You also have to think about where to release them in your simulation. And this is done, again, in Cell Blender. You use the graphical user interface, but it's done by creating release sites. These release sites have a shape. And so, for example, in this case here, we release volume molecules in a shape that's called world cube, basically within our cube. This is just a naming. So what this says is I want to release 2,000 volume 1 molecules in the whole cube. So this is the simplest thing you could do, right? Now for the surface molecule that we've defined up here, we'll do a little bit something different. So in this case, we release it on the top surface of our cube. So this is what this syntax means. So in the case of a cube, we can release it on the top, on the bottom, on the left, or the right. So here we're a little bit more specific. So we release the molecules on the top surface of our cubic cell in this case. Again, 2,000 of them. Of course, it's just one way to do it. So basically, just to show you can release molecules wherever you want. And what wherever you want means depends on the questions that you have. You could release it in a little round patch on the top or at the bottom, or the little compartment inside the cubic cell. So basically, you have complete freedom of where to release your molecules in your simulation. You just have to think about where. OK, so there's one. There's one complication here, perhaps, but it's actually quite a powerful feature, and that comes back. Now we're coming back to this surface normals that I explained to before. So if you release volume molecules, so this is all. This looks. Anybody? Does it make sense to everybody how that's done? We just say where, what molecule, and how many in this case. So the surface molecules, we have one additional thing happening here. You see this apostrophe here. So for surface molecules, we have to also specify the direction with which we actually release these molecules on the surface. And so I'm going to come to that now. So basically, let's think about surface molecules. So this is a surface molecule, or could be a potential surface molecule. This is anybody know what that is? Okay, so this is KCSA, so it's a potassium channel. So it's a voltage-gated potassium channel. This is the pore here. And you can already see that it's not really a symmetric object. So it really has a clear, it has what we would call a top and a bottom domain, right? So it's different here than here. So it has something that we call top and the bottom, right? So top and bottom is our nomenclature. You can call it whatever you want, upper or. And the surfaces have a front and a back. And this goes back to that normal vector. So basically, if the normal vector, if you have a surface here and the normal of the surface goes that way, then this here is the front, this here is the back. Yeah. So we have this. And so that shows you that there's now actually two ways I can put these molecules in the membrane. Right? So I could put it in such that the top domain of my KCSA is at the front of the surface, or I could put it in the membrane such that the bottom domain is at the front of the surface. What that really means for your simulation really depends on what molecule you're placing. But MCell has this powerful capability that you can actually decide which way to put your surface molecule into the membrane. Yes. So the power of that will become, I think, hopefully clear once we talk about reactions, why this is important. Right? And you can actually model quite powerful transport processes across the membrane using this mechanism. And so basically, this is what this syntax here does. So this syntax here tells MCell how you want to place the surface molecule into the membrane. Okay, so basically, if you say it like here, if you give this apostrophe, you tell MCell that you want to place it top front, as we call it. So basically, the top domain of your surface molecule is at the front of the surface of the membrane. If you write it like that, surf comma, then you place the bottom domain at the front. Or you could give it this semicolon here, and that basically tells MCell you don't care. So if you place them, MCell will randomly place them up or down. Okay, so this is basically anytime you place a surface molecule, you have to think about how you want to place it in the membrane. And yes.
So how do you define the top of the? You'll see that
Yeah.
when we show you how you define the reaction.
Yeah, let's wait until we do the reactions. So what that really means, again, is it's not. It depends on what process you're describing. So maybe when we come to the reactions, it becomes clear.
So for the back, so the question was, how do you define the top and bottom of the molecule? And like the surface molecule, what is the top of the surface molecule?
Yeah.
So that when we show you how
Right.
to define the reaction.
So let's go to the reactions. Writing reactions in MCell is actually quite straightforward. It's basically the way you would expect it to work. So you have the syntax, you have reactants, products, reaction rate, and you can actually name it. And the naming is useful if you want to count reactions. So you can count by name, for example. So here's two examples. You have this reaction, unimolecular reaction, volume 1. Volume 1 molecule goes to volume 2 with this rate. You can also have things like annihilation, where two volume molecules combine and basically disappear. What that would mean in a biological context, I don't know, but it's a possibility, so sometimes that's useful to do. So basically, writing reactions this way is very simple to do. You just need to know the reaction rate constant. That's something you need to know. That's sometimes not easy to come up with, but it depends. Since MCell is a particle-based simulator, you can only define unimolecular and bimolecular reactions. So there's no, you can't do things like you can do in ODEs, that you have higher order things like Michaelis-Menten type thing. So this is not possible using MCell. So you have to break down whatever reaction scheme you have into these elementary reactions, unimolecular, bimolecular. So these are the ones that you need to have. Again, just a reminder, here's the reaction rate constants. So if you get those somewhere from the literature, make sure these are the ones that you have. If not, you need to do some conversion. Okay, we'll come to that later. And so let's look at this this reaction here. So this is a reaction that involves a volume molecule and a surface molecule. So basically volume 1 goes to surface, plus surface molecule goes to volume 1 plus surface. And it looks like nothing's really happening here. But you also notice that now we have all these tick marks here, the commas, apostrophes. And so let's talk about what this really means and what this really describes. So basically, anytime you have a reaction that involves a surface component, a surface molecule, you have to specify the orientation. It's required. You cannot have a reaction that does not have an orientation specification. And this basically tells MCell how you want this reaction to happen. So let's look at the reactant side. So what you notice here, we have opposite specifiers. You have a comma here and an apostrophe here. And if you write it this way, this basically means that the volume 1 molecule will react with the bottom of your surface molecule. So this is what that means. Right? So graphical, volume 1 reacts with the bottom. And if we look at the product side, now these two guys are on the you have the same ones. You have two apostrophes. And this means that volume 1 reacts with the top domain of the surface molecule. If you have this situation, they're opposite. Volume 1 reacts with the bottom domain. If they're the same, it reacts with the top domain. And you can actually see what this reaction actually specifies, right? It's a transport of volume 1 from the inside of this compartment, or from this side of the membrane to the outside, mediated by this surface molecule. So this is basically what this describes. It's a transport process of this molecule across the membrane, mediated by this surface molecule. Okay? And in fact, this reaction describes also this possibility. It just describes the relative reactivity of volume 1 with regard to the bottom domain. So this is equivalent, right? So this again reacts with the bottom, and it is released here at the top domain of the surface molecule. So the way that this reaction happens depends on how you place these molecules in the membrane in the first place, right? If you made your geometry, your cell, and you placed your surface molecules with the top domain to the front of the surface, then this reaction will pump out volume molecules from the inside to the outside. If, however, you designed your simulation such that the molecule was placed that way initially, so when you placed the surface molecule, you said, oh, I want to have it front back, then this reaction will describe the pumping in of volume molecule from the outside to the inside. So in other words, the reaction just describes how the reaction happens with regard to the surface molecule. What really happens in your real simulation depends on how you place the molecules. Right? And so this basically does this answer a question what the top and the bottom is? So you basically, you decide in the beginning, I have this surface molecule, it has a top and a bottom, and I want to model this process. I want to have a process that pumps this molecule from the outside of the cell into the cytoplasm, whatever that is, reuptake of some nutrient or something like that. Then you would place the transporter with its bottom domain at the front of the surface and write the reaction like that, and then this process would happen. So in other words, you have to think about the process first. So you draw some pictures, you draw your cell, you think, I want this process to happen, goes from the outside to the inside, or whatever is going on, and then you translate that into the right kind of syntax. And you even have to do this if you use Cell Blender, because even in Cell Blender you have to specify orientation. It's not obvious. I mean, the tool doesn't know how you want that reaction to happen. So this you actually have to do always. You have to think about, here's my geometry, here's my reaction network that I have. How do I want this to happen when mapped on my geometry? What are the transport processes? Where are things happening? Are things going in from the inside to the outside, from the outside to the inside? And then you can decide, okay, now how do I have to actually place my surface molecules in my geometry, and how do I have to define my reactions using these molecules to actually map that onto the reaction network that I have. So that's usually, so I think drawing these pictures is actually a very good idea, because this is actually a simple case, right? It's just a simple one transport process. It's already a little bit tricky. I mean, if you think about it, you have all these tick marks. So I like to draw these kinds of pictures. Just once you have those drawn, it's very easy to translate them into either the MDL or putting the right tick marks into Cell Blender. But you have to think about this a little bit. And we have, and this is probably one of the most complex things about designing reactions in M-Cell. We have some additional documentation on how to do that on our website, and we can also talk about this more. So I realize that this is tricky, so it takes a little bit of getting used to. But hopefully once you do it more, it'll become clear how that works. I actually once in a while get confused myself, because if you have complicated geometry, it's not so trivial to keep everything in your head, so it's good to draw pictures.
And we'll say this over and over again, it's one of the complications that comes along with needing to deal with space.
Mm-hmm.
If you're doing spatial simulations, there is an inside and an outside of your compartments, and the reactions have to be specified in a way that takes that into account. And this, I think, is probably the best way to do it, and by drawing these pictures. At some point in the future, in a future version of Cell Blender, we might, in the GUI, we might have a way to construct these things visually.
Yeah.
But for now, you have to do it by typing it in yourself into the interface. And Marcus has said it, and I'll say it again, that drawing these little pictures is really helpful.
I mean, the reward for this kind of capability is really you can model very complex reactions involving surfaces, transport processes. So you have a lot of flexibility. So there's a lot of things you can model with that simple syntax that involves, compartments, different topologies, transport. So it's quite a powerful way to model probably most of everything you want to throw at a simulation like that. So I don't think we've encountered much that you couldn't really do using this kind of syntax. Although
you can even write reactions where the result of the reaction is that the surface molecule that you're talking about flips its orientation before and after the reaction. The result is the surface molecule, like this potassium channel, ends up flipping itself in the membrane. Now, why would we do that? Why would we need a syntax that can allow that? Well, it turns out that there are these protein molecules, transmembranous proteins called flipases, that exist in nature, or proteins that diffuse around the membrane, and when they encounter a protein molecule, another transmembranous protein of the right type, it interacts with it and flips the orientation of that molecule in the membrane. So, nature has discovered also that it needs to be able to control the orientations of molecules in its own membranes, and because of that, so do we when we want to simulate them.
Right. Okay, so this was, if this is not crystal clear to you, that's just fine. But just to tell you that there's, if you want to have, if you have surface molecules in your simulations, you really have a lot of capability here to model all sorts of different processes, reaction processes or transport processes going on at the surface. So before we break, there's two things I wanted to just briefly mention. One of them is something that we call partitions. And so this is something that you can do in CellBlender and or in the MDL if you write it yourself. And so this is basically doesn't have any impact on the correctness of your simulation, doesn't change any of the numbers that you have, but it's sort of a tuning strategy to make your simulations run faster. And it's particularly for large models with many molecules, this is really key. So that's why I mentioned it. So this is really something, as soon as you have a little bit more sophisticated model, you gotta spend some time with partitioning. And what this basically does is it subdivides the simulation volume. In this case, it's a sphere, but it could be something much more complicated, into little spatial partitions and spatial subvolumes that make your simulation run much faster. Simply because when MCell looks for, when particles diffuse, for example, and look for reaction partners, they don't have to look at every particle in your simulation. They just look at the ones in their subvolume and maybe the neighbors. So it's much more efficient, faster simulation. And so you should, once you start setting up a real production simulation, you should spend some time with this partitioning. And the way that you do that maybe is just to start off with some partitioning scheme. You could have maybe 50 nanometer partition size or something like that. And the best way to really find a good way to partition your system is to start with some partitioning scheme. Then you run the simulation, you write down how long it takes. You decrease the size of the partitions. And if it runs faster, you keep going until at some point you notice it's actually not run faster anymore. And so there's sort of a sweet spot that you can find fairly quickly after running maybe 10 simulations or something like that. That sort of is the ideal partitioning for your system. So there's a little bit of a trade-off here with how fast it can run. And the more partitions you have, the more memory you will need. So at some point you'll run out of memory, or your simulation slows down again because it needs to allocate a lot of memory. So there's kind of a valley at some point, and it takes a few test simulations maybe to find it. So it's not completely automated. So if you have a big simulation, that's worth spending some time doing that. So I'm just saying it's not difficult. You just don't forget about it. So if you have a huge simulation and it kind of chugs along, it's kind of slow, you can probably speed it up, factor of 10 to 100, doing a good job here. So don't forget about it.
Is there a way to assign these partitions in CellBlender?
You can do it in CellBlender, right? It's just not automated. You have to do it. So the default that you might get might not be optimal for your system. So we should probably come up with a better way to do that, a little bit more smart. But for now, it's not difficult. It basically just, you have to remember it. You pick something that looks reasonable. You run a simulation, and you can take more fine-grained partitions. If you notice it still speeds up, then you just keep going until at some point you notice it kind of peters out.
So how do you deal with the dependencies?
Dependencies?
Yeah, with
you don't have to worry about this at all. It's all taken care of you. So it's
You don't even have to
yeah,
think about it.
yeah,
And partitioning won't even change the numeric result
yeah.
of your simulation.
It's pure efficiency thing. So it's just some people forget about that this is a good thing to do. This gives you a real speed boost if you have a big simulation. So this is, I think, the final slide, maybe. So basically, one of the key things in terms of output for your data, so the number one key thing is visualization, output, and that you can just look at in Cell Blender, so I won't talk about this here. So you basically run your simulation, you have your 5 compartments, you put molecules into compartment 1 and 4, and you expect that you get some transport process between the compartments. You run your simulation, you look at it, and you convince yourself that your simulation actually does that. So that would be step 1. And you realize, oh, I put this molecule in the wrong way in the surface. So instead of pumping it in, it pumps it out. So you typically notice that right away when looking at your simulation. So that's why it's so important. It's very easy to confuse the comma with a tick mark, and all of a sudden your process goes the other way and everything works a little bit not the way you thought it should work. So look at it and make sure all the transport processes, all the reactions happen in the right compartment and things are going the correct way. So look at it very carefully. So that's always a good thing to do. And then the second kind of output, and so this is what we call reaction data output, is typically consists of these count statements where you can count all sorts of stuff. You can count the number of volume molecules in the world. The world means the whole simulation. And you can count the number of molecules basically in any geometry you have in your system. You can count it in your cell, in your subcellular compartment. Often people just add what we call sampling boxes. It's just a transparent box that you can put anywhere in your simulation just to sample what's the number of A molecules in this spatial region and here and here and here. And so you can kind of investigate maybe your concentration profile in your cell as the simulation progresses, whatever your question is. So you basically have almost infinite freedom of counting and tracking whatever kind of molecule you're interested in, either in the volume or on the surface. So you can really, with the syntax and also from within Cell Blender, you can specify very complex tracking schemes of molecules. You can count all the reactions that happen. So it's a very flexible language to basically count the kinds of things you're interested in. By default, you don't get any output, so that's what confuses some people, because it's just not clear. There's no good way for us to get a good default. I mean, if you have millions of molecules, you may not want to count them all. So you basically have to decide what interests you. So there's no good way for us to just count something, because it could be your model could be very complicated. You have all these geometries, molecules, and some of them. So there's no obvious way to count for you. So basically, if you don't specify any reaction data output, you don't get any, which may be fine. Maybe you just want to look at your simulation. That's OK. But basically, in this part, you have to think about what am I interested in? What do I want to know about my simulation? And so you can specify that very fine-grained. It might be as simple as just how many A molecules are there in my simulation. It might go all the way, how many A plus B molecules are in this little spatial regions right next to my transporter molecule, because that's what I measure experimentally in my fluorescence microscopy experiment. Whatever your question is. So you can all define this nicely with this syntax. OK, so I think this is basically all I wanted to talk about. So this was a very quick intro into MDL. Again, if you use Cell Blender, you don't see a lot of these things, but there's some aspects you need to think about. Most importantly, things like where things are and how reactions happen in your geometry, what the orientation is, what the spatial aspects are, how molecules flow through your simulation. That's something you need to think about before you actually write down these reactions typically. Okay, so are there any questions? Yes?
One question I had was, is there any way to parallelize this, or is it all just serial at this point?
There are certainly ways to parallelize it. So there's MCell right now is still serial code. We're working on a parallel version. However, there's lots of opportunities to parallelize your simulations. So one of the things I haven't really touched on here, maybe I should have, is that so this is a stochastic simulator. So basically, when you run your simulation, so it uses random numbers or pseudo-random numbers. And so when the simulation runs, you actually give it a random number seed in the beginning that seeds the simulation. So in other words, if you don't give it a seed, it picks seed number 1. So the key thing here to observe is if you run an MCell simulation, it's basically you have to think of it in a statistical way. It's one possible instantiation of your statistical distribution that describes your model, right? I mean, if you run it once, you basically have one possible outcome of your simulation, and typically to actually get your data, you need to run more than just one. You need to run a large sample. You need to run 1,000 of them, take the average, look at the deviation. So that's what you typically do. And this step can be parallelized. So you can run, depending on your setup, you can run hundreds of seeds at the same time. So this process is sort of embarrassingly parallel.
But within each seed, you cannot kind of compartmentalize, you cannot kind of distribute.
No, so a single simulation right now is still a serial run. Typically, that don't take that long unless you have a really huge model. So it can take long.
So that's still serial.
Mm-hmm. But we're working on a parallel code, so at some point that will be possible. But it's a good. You remind me of something that I should have maybe mentioned. So keep that in mind if you run an MCell simulation. Again, it depends on your model, but it doesn't necessarily make sense to just run one simulation, look at your output and say, aha, it is 5, because it's just one. It's a stochastic process, and so you really should, most of the time, do some averaging of the quantities you're interested in. Again, it depends. So some models, just one run is sufficient if you can do temporal averaging. But if you're counting the number of bound receptor molecules in this region, then you might need to run a couple hundred simulations to really get a good average number of bound molecules to your receptor molecule, plus the standard deviation perhaps. And how many you have to run is really depends on the process. It's sort of, you have to decide how large your n has to be that you have good statistics. It could be small, it could be large, it could be very large. And also keep in mind that MCells, if you don't specify, if you want to do this sampling, you have to actually specify different random number seeds. So if you just run MCell 1,000 times, you get 1,000 times exactly the same simulation. So that's not, that is sort of a pitfall. So if you need to sample, pick different random number seeds. So the seed number 1, 2, 3, 4, 5, however many you need to go. Then you get statistically independent simulations, and then you can do your statistical analysis. If you just keep running MCell 1,000 times, you don't get any averaging really. The nice thing is these simulations are reproducible. So despite their randomness, if you run MCell today on your simulation and next week, you'll get the same result. So it's totally reproducible. Are there any other questions? Okay, so why don't we make like a 15-minute break, coffee break, whatever, bio break, and then we'll come back.